Welcome to This Explainer. Today, we're basically going to turn you into an everyday scientist using completely normal household items to wrap our heads around the fundamental concepts of time and speed. I mean, have you ever stopped to wonder how people accurately track the world around them before we had, atomic clocks, digital stopwatches, or the GPS speedometers on our phones? Well, today, we're going to strip away all that modern technology and unlock those mysteries using just the physical world around us. Let's dive in. So let's start with a bit of a puzzle. Picture this. You're trying to accurately time a 100-meter sprint in the ancient past, way before smartphones or even mechanical watches were a thing. If you're standing there watching a runner across the finish line, how would you possibly know their exact time? You couldn't exactly just glance down at your wrist, right? Early humans had to look up. They started noticing that certain events in nature, like the rising and setting of the sun or the shifting phases of the moon, they kept repeating themselves after definite intervals. And those natural cycles, they became our very first calendars. But what about measuring smaller fractions of a day? Now that required some serious ingenuity. To pull that off, our ancestors tracked time by building these absolutely ingenious devices just to capture those natural rhythms. Take the sundial, for example. It figures out the time based entirely on the shifting shadow of an object under the sun. It's brilliant. And then you have the classic hourglass, which measures time through the steady, physical flow of sand dropping from one glass bulb down into another. Think of these as essentially the smartwatches of the ancient world. Now, to show you just how incredibly precise these early scientists got, get this. The world's largest stone sundial, called the Samrat Yantra, was built about 300 years ago in Jaipur, India. And it is massive. It stands an imposing 27 meters tall. Because it's so huge, its shadow actually moves at a staggering speed of about 1 millimeter per second. It literally moves fast enough and falls on a scale so finely marked that it can measure time intervals as short as 2 seconds. I mean, that is astonishing accuracy for a device made entirely out of just stone and sunlight. But as you might guess, sundials have one massive flaw. What do you do when the sun goes down? Or if you're stuck indoors? Well, to measure smaller intervals at night, people used water clocks. Instead of tracking light, these relied on the incredibly predictable sensory drip, drip, drip of water. In one version, water flowed right out of a vessel that had specific markings for the time. In another version, a small floating bowl with a hole in the bottom would gradually fill up and sink after a very fixed amount of time. And here's the fun part. You don't need a time machine to really grasp how this works. You can think like a scientist and literally construct your own right at home. Just grab a standard plastic water bottle. First, carefully cut it roughly in half. Next, just use a pin to pierce a tiny little hole right in the bottle cap. Then take the top half of the bottle, flip it upside down, and nestle it neatly right into the bottom half. Finally, fill that top part with water. You can even add a drop of food coloring to make it easier to see, and use your modern watch to mark the water level on the bottom plastic every single minute as it drips. The absolute magic here is that once you've marked those water levels, you've successfully built a working physical timepiece out of everyday trash. No joke. To use it again, you just pour the water back into the top. Every single time that dripping water reaches one of your pen marks, you know for a fact that exactly 1 minute has passed. You have quite literally harnessed the steady flow of matter to track the invisible flow of time. Okay, but the real breakthrough in mechanical timekeeping came in the late 1500s. And it's a great story. The famous scientist Galileo Galilei was supposedly sitting in a church when he noticed a lamp suspended from the ceiling just swinging back and forth. Since he didn't have a stopwatch, Galileo did something brilliant. He used his own pulse to measure the time it took for the lamp to complete a single swing. And he realized something incredible. Whether that lamp swung in a massive, wide arc or just a tiny, narrow one, each complete swing took the exact same amount of time. That single, simple observation birthed the pendulum clock, which completely revolutionized how we measure time. And the best part? You can recreate Galileo's genius right now in your living room. All you do is tie a heavy metal ball or even just a simple stone, what scientists call a bob, to the end of a string that's about 150 centimeters long. Tie the other end to a rigid support so it hangs completely freely. Wait for it to settle, and then pull the bob to one side, an extreme position, and just let it go. It'll immediately start to swing back and forth in a beautiful, periodic, repeating motion. Now, if you experiment with this simple pendulum, you're going to discover a fundamental rule of physics for yourself. If you change the length of the string, the time period changes. Make it a shorter string, it swings faster. Make it longer, it swings slower. But here is the crazy part. If you keep the string length exactly the same but swap out your stone for a much heavier one, the swing time doesn't change at all. Actually, let me reiterate that. The mass of the bob literally does not matter. Only the string length alters the time. That constant rhythmic swing is literally the heartbeat of every single grandfather clock ever made. All right, so now that we have a firm grasp on how to track time, from ancient sundials to dripping water to swinging pendulums, it's time to shift gears a little bit. Because time, by itself, is really just a ticking clock. The real magic happens when we combine time with distance. We have to ask, if we know how to measure time accurately, how do we use it to compare the motion of different objects? Essentially, how do we calculate who or what is actually the fastest?
Well, the answer is speed. Speed is the mathematical bridge between space and time. It's simply a calculation of the total distance covered by an object divided by the total time it took to cover that exact distance. In the scientific community, we typically measure this in standard units, like meters per second. But for larger distances in your day-to-day life, you're probably way more familiar with seeing it as kilometers per hour or miles per hour when you look down at a car's dashboard.
Let's look at how this plays out in the real world. Imagine a student. Let's call her Swati, and she's riding her bicycle to school. Now, she knows her school is exactly 3.6 kilometers away from her house. She checks her watch right when she leaves, checks it again the second she arrives, and notes that the trip took her exactly 15 minutes. So, how do we figure out her actual speed? To find her speed, we just need to do some basic standardization. We take her kilometers and convert them to meters, and we take her minutes and turn them into seconds. So, divide that total distance of 3,600 meters by the total time of 900 seconds, and the math clearly reveals Swati is pedaling at exactly 4 meters per second. But hold on, we have to think critically about this for a second. Did Swati realistically ride at exactly 4 meters per second for the entire journey without stopping? Probably not, right? She likely started from a standstill, sped up, maybe had to slow down for some traffic or a sharp turn, and then finally braked when she got to school. In everyday life, speed fluctuates constantly, and this introduces a really important difference in physics: uniform versus non-uniform linear motion. Uniform motion is when an object covers equal distances in equal intervals of time, meaning its speed never ever changes. Non-uniform motion is when an object covers unequal distances in equal intervals of time.
To really see this in action, imagine tracking 2 trains over 30 minutes. Take a look at train X. Notice how it jumps exactly 20 kilometers every 10 minutes, from 0 to 20 to 40 to 60. Boom, boom, boom. That is perfect uniform motion. Its speed is completely constant. But train Y? It behaves very differently. In the first 10 minutes, it travels 20 kilometers. But in the next 10 minutes, it only goes 15 kilometers to hit that 35 mark. Then it travels another 15 to hit 50. Train Y is in non-uniform motion because the distance it covers in those exact same 10-minute chunks is constantly changing. In the real world, almost everything moves non-uniformly, and that's exactly why when we calculate speed, like we did with Swati, we're almost always calculating an average speed.
So, to wrap up this explainer, I really want you to step outside today and just look around your daily commute. Whether you're hopping on a bus, walking down to the local store, or even just watching the clouds drift across the sky, ask yourself how distance and time are constantly interacting all around you. You don't need a lab full of complex equipment to figure it out. Just a simple understanding of distance, a steady beat of time, and the curiosity of an everyday scientist. So, the next time you step outside, ask yourself, in the giant moving equation of the universe, what average speed are you traveling at right now?